So it's my pleasure to have George Moeller here. George has a PhD in mathematics and is currently on the faculty at Indiana University, Purdue, in computing and information science. Is that the right one? Right title?
Yeah, it's pretty much computer science department, but yes.
And he's been phenomenally active in coming up with methods to use computational and CS methods for predictive policing, as well as analysis of spatial aspects of hotspots. And so we're really, really pleased to have him here. So, George, thank you for coming.
Thank you. So, you know, when I was asked to give this talk, Andrea Bertozzi and Martin Short asked me to give this, and they've kind of, you know, heard a lot of the talks I give, or they're on the papers. So whenever they invite me to something like this, I usually try to put all the stuff that they haven't seen into a talk, which is kind of this random name. Then they're not here, and a bunch of people I don't know are here. So I kind of redid the talk. But I think some of this should hopefully be relevant, and it'll be at a bit more of a micro scale, which I think is useful to look at. So I got interested in this. I was in a math department, and Martin and Andrea were using PDEs to model crime hotspots. And Martin actually made this movie. This is of gun crime in Chicago. And these hotspots will form, and they might stay there for a while and move somewhere else. And we were interested in modeling those dynamics. Kind of another way of thinking about it, and this is David Weisberg at George Mason, is that he has this law of crime concentration, which says a large percentage of events occur in a small percentage of the city. So, for example, 50% of crime occurs in 4% of the city. You can look at a lot of different types of events, and they follow a similar kind of law, if you want to use the term loosely. Recently we were looking at opioid overdose deaths in Indianapolis, and about 50% of those occur in about 5% of Indianapolis. These hotspots are overlap quite a bit with violent crime hotspots in the city. And then this has been done for actual firearm incidents. So this is Andrew Papachristos, one of the organizers, and Braga. 37% of firearm incidents in Boston and about 1% of street segments. So a lot of these incidents are highly concentrated. There's a lot of reasons why this might occur. So sometimes it's contagion. So this is East Lake and Clover Street in Los Angeles and in Hollenbeck. This is the times of attacks between those two gangs. You have gaps with no violence, and you have these highly clustered series of events that can't be explained by a Poisson process. But other reasons exist for concentration of crime. For example, this residential burglary can only happen where you have houses, and you get concentration because of that. And there's a lot of other reasons as well. Just kind of an overview of my research over the last several years. Kind of the way we're kind of framing it is trying to build software systems to match people to place and time and risk for intervention. So it could be an officer patrolling burglary hotspots when they're not on a call to service. It could be repositioning ambulances in Indianapolis every 30 minutes to more quickly respond to medical emergencies. So the outline of this talk, it's kind of 2 or 3 separate kind of problems that I think maybe are related to gun crime or gun violence. I'm not an expert on gun crime or gun violence, but I think some of these ideas may be useful. So the first one I'll talk about is ranking, which kind of gets at this idea that David Weisberg has. So when you calculate one of these statistics that is his law of crime concentration, there's kind of a problem you run into, and we ran into this when we were trying to look at opioid overdose concentration, because we only had 1,000 events in about 5 years. And at the extreme end of like having limited data, this is the problem you run into, is that if you have one single event, right, and you can chop up the city into maybe a grid or street, you can use street segments. But in this case, 100% of the events is in 4% of the geography. And if I had decided to, instead of using 25 grid cells, use 10,000, then 100% of the events would have been in 1/10,000th of the geography. But there's something, about this that we would want to do. What we would really want to do is, observe this for a long period of time, as long as you need, and eventually events would build up in some of these cells. And then in kind of the limit, as you go to infinity, you'd want to compute this law of concentration. I'm not going to claim that this is new, but this is I think, a problem that comes up in the criminological literature a lot that is not always addressed in the right way. So I thought I would talk about it here. So first of all, this is kind of well known in other fields. So what this law of concentration really is, it's a point on the Lorenz curve. So, and what we're really doing is we're ranking hotspots. So you take every area in the city and you rank them somehow. A lot of times it's just by the counts, but it could be by something else. And then you look in the top, percentage of the city, and you look at how much crime is captured there. If you take the area under that curve, you get what's called the Gini index. This is kind of like the average of crime concentration. So if we kind of use these standard summary statistics, like the ones I presented on my first slide, turns out they're very biased because of the reason I just showed you. And we need to kind of make our mathematical assumptions explicit to correctly estimate the concentration of these events. So here's another way of looking at it. If I just take a synthetic model, so suppose every area in the city is a Poisson process with a different rate, but it's just fixed. It's stationary. It's not changing in time. And then I just start observing that Poisson process. Well, if I use these kind of standard estimators for low event counts, then I'm going to highly overestimate that I have some concentration of events, and only kind of as I increase my data set size do I get the correct estimator. And even in the Journal of Quantitative Criminology, there's been some efforts to kind of mitigate this, but some of those actually are incorrect. Like there's one called the adjusted Gini index that actually goes to 0 as the data set goes to 0, whereas you really want to estimate this true value. So we kind of have a simple method that we've been using to correctly estimate the law of crime concentration. So it goes kind of like this. You estimate a negative binomial to the counts of the data. So we heard about the negative binomial in the last talk. Negative binomial is good because it can model over-dispersion in crime data and other types of event data. And then what you can do is you can use the fact that the negative binomial is really a mixture of a Poisson process and a gamma distribution. So this rate in each neighborhood that's fixed, we're assuming that distribution is a gamma across different neighborhoods. And then once you estimate that, now you don't have this issue of a bunch of cells having 0 counts. And we can use like numerical integration to estimate the law of crime concentration. So why do we care? Well, here's kind of an example of why you might care. So here I'm applying it to gun crime concentration in Chicago. And if we just kind of use these standard estimators, then you might say that homicide with a gun is fundamentally different than battery with a gun. These are statistically different. But if you use this Poisson gamma kind of correction, then they're no longer, at least statistically, different. They're within the margin of error, which kind of makes intuitive sense. In some sense, a battery with a gun may be different, and a homicide just because somebody died, but not because of the situation. The situation may be very similar. Now, what about self-excitation, though? Crime and other types of events aren't stationary Poisson processes. So these may have actual contagion in them. And so here's the Hawkes process model again. So now we can imagine crime is a stationary Poisson process that generates, spontaneous events, but each of those can trigger events nearby in space and time. So these background events, they might be spatially varying, but stationary in time. But then as an event occurs, the rate of crime goes up by amount g, and it decays in space and time according to this kernel. So you get these clusters of events that act as like a branching process. So an event triggers another event, and that can trigger other events after that. So the problem with measuring crime concentration, if crime is a self-exciting point process, is that if you only observe for a small period of time, then it gets worse because you'll have the initial event, and then in that neighborhood it'll spawn a bunch of offspring events, and you'll overestimate the crime concentration even worse than the first example I gave. And so you have to wait a longer period of time to get an unbiased estimator with just like kind of the standard sample statistic. So what can you do? Well, the trick is to estimate this branching structure between events. So it turns out if you fit one of these models, you can estimate the probability that event I triggered event J. It's just given by the ratio of this G kernel over the overall intensity. And then what you can do is you can thin the data with these probabilities and try to get an estimate of just the spontaneous events. And this is what seismologists do to try to get long-term estimates of seismic risk, is they try to remove the aftershocks from catalogs and just use the background events. So we can do the same thing, and here's kind of the result you give. This is just on synthetic data. But here's like the true Gini index and the number of events we're using. And even if we use kind of our Poisson gamma estimator just on the data itself, it's way off in terms of measuring concentration. But if we decluster the data set and then run this kind of Poisson gamma estimate of concentration, you get something close to the actual value you're looking for. What if we want to take this a step further? So like I said, what we're really doing here in Weisburd's law of crime concentration is we're ranking neighborhoods in the city. And then ideally, if you're talking about hotspot policing, you want to send police to the highest risk locations to do some sort of intervention. And the idea is if crime is highly concentrated, you could have a big impact with limited police resources. So really what we want to do is we want to maximize crime concentration and just the amount of kind of hotspots we can afford to send police to. So this sort of problem arises in information retrieval. So if you're Google, you want to maximize the relevance of your search results on the first page, where you don't really care how good your model is on page 100, because nobody's going to make it that far. And the same kind of thing is true with crime hotspots. You might be willing to sacrifice accuracy of your model at kind of a mid-risk hotspot if you can maximize your crime in the highest risk areas. There was a 2017 National Institute of Justice forecasting competition to try to do this exact thing. In particular, in Portland, Oregon, you were asked to maximize the amount of crime given you could only make a certain number of predictions in Portland. And then different teams competed. So we've kind of borrowed methods from information retrieval to do this. So the problem, again, because this is a ranking problem, this law of crime concentration, or sometimes it's called PAI, which just normalizes by the area you're predicting, it's non-differentiable. So because you have to sort these cells, that sort makes this loss function non-differentiable. So what you can do is you kind of model a pseudo gradient of the loss function. So the way it would work is, suppose I have some model that maps features in this area to a score, and that same model maps these features to that score. And now given that current score, I can rank all these cells. And then I can compute the PAI, or the crime concentration there. Now, what you do is you swap, for every pair of hotspots, I and J, you swap their ranking, and you look at the change in the PAI, or the crime concentration, that you get when you change that ranking. And you get a delta in the ranking here, and then you multiply that by this logistic function, which kind of adds a margin to your model empirically so that it generalizes to new data better. And so what's going to happen is when cells are ranked incorrectly, they're lower ranked, but they really should be ranked higher. This is going to kind of push their gradient up so their score increases. And then you need some features in your hotspots to map the environment or what's happened recently to these scores. We've kind of used these Hawks processes as features, so we generate a bunch of Hawks processes with different parameters and then feed them into this model, or you can use kind of count-based features of events. And then the third kind of thing that's important if you want to maximize crime in your hotspots is you kind of maybe need to get away from fixed grids or other kind of standard polygons that you might use to create these hotspots. So for example, in this kind of simple example, if I just use a fixed grid, I might only capture 50% of crime in my hotspots. If I'm willing to go off grid, I could capture twice as much crime. And it sounds simple, but these might be globally different hotspots depending on how you choose these polygons. Or you might let them rotate or take on different shapes. So kind of putting all this together where you kind of learn to rank these hotspots and you mess with the polygons you're using to capture crime in them, you could actually get up to about 35% more events in your hotspots. And this kind of method we use, this is joint with Mike Porter at Virginia. This method was tied for first in this competition. Or kind of a sub-method that we used for that within the rules of the competition. So I'm going to end this section on ranking with this slide. So I'll point out Charles Leffler in the audience. His team tied with us, I think, for first place in this competition, not using self-exciting point processes, but using log Gaussian Cox processes. A log Gaussian Cox process, essentially the intensity follows a Brownian motion and will generate clusters just like a Hawks process would. So you just visually, it's hard to tell if you have a Hawks process or something that's really just correlation. And Charles also has a paper on looking at gunshot data from ShotSpotter where he doesn't find contagion in that sort of data. So just kind of to leave you with this, I don't have a solution, but what I will say is it's very hard to untangle contagion versus other types of correlation in these spatiotemporal data sets. So I think that's somewhat of an open problem. Okay, so the next thing I want to talk about is kind of what do you do with these models. So in terms of interventions, we've done a few things or are working on a few projects. This is an older one that we ran in Los Angeles. It was focused on burglary, and we did it in 3 divisions in Los Angeles. And the goal of this experiment was to kind of put one of these point process models head-to-head with a crime analyst. So each day, the analyst made a set of predictions on a Google map, and our algorithm made a set of predictions on a Google map. And then we randomly chose to give one of those to officers in the field. And here was kind of the results we got out of that experiment. So this is not maybe too surprising, but the algorithm was about 2 to 3 times more accurate at putting events in the hotspots than the analyst. So kind of going back to this law of crime concentration, the point process had 2 to 3 times more events in the hotspots than these analysts. Why is that the case? I mean, this kind of goes back to kind of, I think, related to like stock market prediction, where a lot of kind of investors will chase what happened yesterday, and crime analysts kind of tend to do the same thing. So if you kind of look at a 1-month hotspot map of where crime was occurring, that almost directly correlates with what the analyst was doing in terms of placing their predictions down. The algorithm was much more focused in certain areas than the analyst. So we'll probably be talking a lot about contagion over the next maybe couple days, but in fact, it's really this background rate that gives the point process the advantage over the analyst. The analyst is kind of overcompensating towards contagion, but it's really this background Poisson process that was kind of focusing these police efforts. Then the question is, it's great if you can predict where maybe these hotspots are going to happen, but do you have enough resources to actually do an intervention? And in our experiment, we kind of just let officers do what they would normally do. So in LA, they have to kind of jump around from call to call. So it turns out, on average, they only have about a half an hour a day they can spend in a hotspot. Even with that limited amount of time, in this experiment at least, they were able to get a 7% reduction in burglary and auto crime, patrolling about 1% of the city for a half hour a day. If you have enough resources to patrol longer, so in the Philadelphia Foot Patrol experiment, they were sending cadets into these hotspots for 16 hours a day, they got a much greater crime rate reduction. Another experiment we might hear about later that was more focused on people, like a hot list of people rather than place. There was at least no difference between treatment and control in that experiment, but it's possible that the officers were just not using the model to the extent that you would need to see a difference. The next thing we're trying to do in Indianapolis is do a social harm hotspot experiment. So police officers have to deal with a lot of events besides crime. In Indianapolis, they have to deal with opioid overdoses. A lot of them are carrying Narcan, and they're pairing them with paramedics in certain areas. Traffic crashes are a big source of kind of social harm in Indianapolis as well. So we have a grant to do a harm-based experiment. So we're randomizing patrol beats in Indianapolis, and then we're going to A/B test harm spots, which try to kind of weight the severity of events in terms of their societal cost against kind of traditional crime hotspots that police departments use, to see if we can have a difference, at least in terms of these other types of events. Can we have an intervention that actually reduces the propensity of them? This is the last thing that we're doing. A part of that experiment is looking at community attitudes towards using predictive models for policing. There's a lot of debate right now about whether we should even be using kind of technology and algorithms to police. So we want to kind of gauge the community's attitude, at least in Indianapolis, towards using these methods. Another project we're working on in Indianapolis right now that I think is relevant to this topic is ambulance optimization. And this is a very old problem. A lot of people have worked on this, hundreds of papers on this. But it was interesting to me that when we kind of met with Indianapolis EMS, Emergency Medical Services, they were doing nothing. So they just park a vehicle at the station and wait for a call to come in. And then that kind of led us to do a national survey. And about 81% of US EMS professionals surveyed, they don't use any dynamic allocation. Now, some of the private companies do, but a lot of the city government EMS departments aren't really using predictive analytics. So we decided to build an application for the city of Indianapolis. And we try to do it in a kind of, it's as a software engineering project where we open sourced the tool we made so that other developers could use it. And a lot of kind of software apps need urban logistics. And you could imagine, city departments, a lot of cities have gunshot detection sensors around them. So where to position first responders, around those could be another example where you could use this. Kind of the problem with using these Hawks processes is they're expensive to train. you have to it's order n squared, where n is your number of events, because you have to look at pairs of events and whether they caused each other. So they don't scale very well, typically. So we had to address that issue in that project. And again, we wanted to create this model API that developers could use, where if you're getting event data in, you just push it to this with an HTTP call, and it'll retrain the model with that event. And then every time you need to reposition your vehicles, you have another API call that you can make, and you'll get the optimal locations of where you should send your vehicles. Mathematically, how we're doing this, we have some ways of estimating these Hawks processes online, meaning you only see each event once, and then you can throw it away. So it kind of gets rid of this order n squared computational issue. And then the second thing is once we have an intensity of where emergencies are going to be, we need to optimally position the ambulances to minimize their response time. In particular, the way we're doing this is we're minimizing earth movers distance to the intensity of these vehicles. And this is different than k-means. If you do k-means clustering, each cluster is a different size. But an ambulance only kind of integrates to probability 1. So it's different. It's kind of fundamentally different than k-means, and it ends up being a non-convex optimization problem. But there's fast methods to do this, so you can use those to solve that in about a second. So you can do this in real time or near real time. And at least in our simulations, we've seen a 50% reduction in distance to emergencies compared to the current station. So we're running an experiment this summer to validate this software application. Some other research groups that have done this have been able to reduce both the response time but also the pre-mortality rate when driving to the hospital using dynamic allocation. This is kind of what the app looks like. So some ambulances may be unavailable and some may be optimizable at any current moment, so it tries to figure those things out, and the commander can kind of make changes to it, so there's kind of a human in the loop if it doesn't place the ambulance in a reasonable location. So the last topic, and this is a little bit off topic, but recently we've kind of done some work on gunshot detection, so that's why I kind of put this in here. But really, this embedding means I have some data that's high dimensional, and maybe it's structured. So the original application we were looking at was human mobility data. So trips in a car, you have a GPS trajectory. And now what if I want to compare one trajectory to another? Again, you can do something like some earth movers type distance to compare those. Or what if I have an image and I want to compare it to another image? It's useful to be able to embed this kind of high dimensional data into a Gaussian space or a Euclidean space where you have an easy distance metric. So the application I'm thinking of is as follows. So I mentioned these gunshot detectors that are around certain cities. ShotSpotter is the main company that sells them. And the way it works is you have like a clip of audio. This is a gunshot. It goes into some kind of low-pass algorithm that says, yeah, this is at least a decent chance this is a gunshot. And then it goes to a team of human analysts that listen to it and then decide, yes, this was, or no, it wasn't. And then they dispatch police to that area. And there's a few things wrong, I think, with this approach. I mean, for one, there's a lag, here that it could be significant. And so you may want the algorithm to just directly send police or other first responders if you detect a gunshot. The problem with this approach is that these models aren't at least good enough yet to have low false positive rates. So firecrackers will often trigger this sort of gunshot flag. So ideally what you would want is something like this, where if the algorithm was highly confident, you just directly dispatch it. And then if it's low confidence, then you send this to the human analyst, and then they can dispatch police or not. And in general, this is kind of an area I'm interested in, and I have a colleague that's interested in non-exhaustive learning. You build a predictive model on a data set and it does really well on that data set, but as soon as you deploy it, things go wrong. And oftentimes you encounter new classes of data you haven't seen before when you deploy a model. So we might have trained this on 100 types of guns, but what happens when there's the 101st type of gun that we didn't have in our training data set? So kind of what I'm going to talk about now is kind of how do you kind of basically find these anomalies that you want to send to the human analyst. I'm not sure if you're familiar with generative adversarial networks. I think this is kind of a neat model. And there's alternatives you could use to do what we're doing, but this is what we're using. The way these work is you have some data that you want to create a generative model for. So here it's handwritten digits. It could be mobility trips in a car. It could be gunshot clips of audio. And so we have two neural networks. One is a discriminator. It tries to figure out what's fake data from our model and what's real data. It's a binary classifier. And then we have a generator neural network that maps noise, just like a 100-dimensional Gaussian vector. That goes through here and it generates these fake examples that the discriminator tries to distinguish. And then they kind of compete in this game, and eventually you end up learning a good representation of your data. So we've kind of extended this framework to do anomaly detection in human mobility. So the idea here is you have this generative model that maps noise to these fake trips in a car, but you also simultaneously learn an encoder that maps the trips back to this latent space. Now, when you do this, it turns out that even though this original Gaussian vector was, had a single mean and variance, when you take real data and map it back through the encoder, it's multimodal. So if you want to do anomaly detection, you really need to use a multimodal model. We're using an infinite Gaussian mixture model that will take a bunch of Gaussians, figure out how many of them you need, and then you can use like a Mahalanobis distance to detect outliers or anomalies in your data. Just to give you an idea how this works, here's some example fake trips in a car. These are the velocity profiles of the car too. The left column is real data, and then all the other columns are fake data. So the thing that's good about this sort of model rather than like an autoencoder is an autoencoder, you don't have a good way of check to see if your model learned a good representation of your data. Here we can visually just inspect it. And once the trips start looking good, you'll see the accuracy of your model greatly improve. Kind of the application we were interested in, I used to work at a car insurance company that had a device in the OBD port of the car, and we would get people's cars would be stolen, and we'd find them for them like a couple days later in San Francisco. But you would kind of want maybe a tool that would immediately know this person is somebody that doesn't usually drive this car, like within the first minute. So here's kind of an example of that, where you have like this person and this is their driving pattern in this latent space or this embedding, and here's this hidden driver or who's stealing your car. It's easy to see it in this kind of space you embedded the data. So what does this have to do with gunshot detection? Well, I have a student that's been working on this for the past few months. Basically fitting these GANs to gunshot audio. And it's pretty, I think good at, how it's worked. So here's like a real gunshot, and then here's a fake one right there. It's hard to tell the difference between the two. So once it's learned this, and it's not easy. It took him a couple months to have these sounding good. But once it does sound good, your model has a good representation of the data. And we can take those embeddings, feed it into a classifier, and we get high 90% accuracy on distinguishing types of gun with these neural networks. Kind of what our plan to do next. It's set to the trigger, sorry. So what we hope to do next is build a low-cost gun sensor using these sorts of models. We're going to put them directly on the sensor itself. It's pretty easy to do, and you can do it for pretty much less than $100. right now, these shot spotter sensors, cities are paying hundreds of thousands or millions of dollars to do it, and the technology really exists to have low-cost sensors. There's some startups that are working on this too. We're not the only group that are doing this. The last slide, this is kind of off. This is further off topic. I just added this yesterday. Thinking about this is a mathematics of gun violence workshop, and there's a lot of mathematical methods and problems I think that are related that hopefully we can kind of think of. So this is my congressional district in Indiana, and I'm right down here in Indianapolis, and there's a bunch of us that are pro-gun reform legislation, but we're lumped in with this huge area, and we have to travel like an hour and a half up here to meet with our congresswoman, who's highly regarded by the NRA. And this is a gerrymandering problem, right? And mathematics has a lot to say about this. John Eck, who's at Cincinnati, kind of calls our research whack-a-mole, where, if you've ever played this game, you're just trying to whack this mole. And the hotspot policing is kind of like this, where it's a short-term intervention. Here's a hotspot, we'll send police, hopefully we prevent the mole from showing up, tomorrow, but it's not a long-term solution. Now, I would counter him that you can win whack-a-mole, you can win tickets and buy stuff with those tickets, but your arm gets tired. This is one example where I think this could if we could fix gerrymandering, I think we would actually go a long way to solve gun violence potentially, or that would be my hope. What other kinds of problems that are seemingly unrelated can we look at to maybe where mathematics could play a role? Hopefully over the next 2 days we can think of some of those to make an impact. So with that, I will just thank a bunch of people. I won't read them here, but these are a bunch of collaborators that worked on these projects with me, and a number of undergrads and grad students were involved as well. So thanks for having me here at this workshop.
So you were using neural networks to basically do classification of these things. Have you tried, so the problem with neural networks is you're right, that you have this problem that if you have something that hasn't seen before, it'll still try to classify it for you. Have you tried something like kernel PDE methods? By PDE, I mean probability density estimation, not partial differential equations. Have you tried kernel PDE methods? Because the benefit of that is that if it's something it hasn't seen before, it just gives it a really low probability.
Yeah, so essentially what we're doing is we're kind of coupling the two. So we have a neural network that generates these embeddings, and that's unsupervised. So it's really just giving its features, and then we're doing just Gaussian kernel estimation here to find these anomalies. So I think it's probably similar to what you're talking about, but you wouldn't want to just feed the raw audio into probably like a kernel density estimate. Like the Euclidean distance doesn't really make sense for the wave signature. Yeah.
George, can you go back to the slide where you had a shot spotter to an analyst to yeah, that's fine. So here's what actually happens on the street. Is there shot spotter? There's a shot, and this goes off. It goes to a human analyst. It goes to the police. Then, if there are outreach workers or interrupters in that neighborhood, the police then call the outreach workers and interrupters and say, listen, do you guys got it? Can you prevent the retaliation? They'll say, listen, we're already there. So the actual, what's happening when when the new workforce is out there is that the police are actually calling these other workers and saying, can you now make sure the situation is
You're
closed?
talking the first responders, like the EMS, or which groups are you talking about?
No, this isn't about, the EMS people are needed because someone is shot and someone needs help. The other thing that needs to happen is that retaliations have to be prevented.
Yeah.
In order to prevent the on-the-spot, on-the-moment contagion of that. That is prevented by interrupters and outreach workers. The only thing is that if those workers were already there, the shot wouldn't have been shot.
Yeah.
But this is what's actually happening now is the police are they won't let you know that. The police chief won't say that at public announcements. But if you were to go to these places where that's happening, they will then call and say, listen, are you guys keeping everything cool? But they'll already know it. And this is part of what is, these methods are fabulous. I especially love two things about this. The ambulance stuff, getting them located best, and also the idea of putting people who can help into multiple problems, which you mentioned about opioids as well as violence as well as all kinds of other things at the same time. But the arrows always pointing to police is not the way it's existing now. It's not, I mean, there's now multiple studies even showing the better value in terms of crime reduction as well as less side effects. I mean,
Yeah.
this is another, this will be the last thing I'll say on this point, is that what's missing from what is called criminology literature, unlike any other literature that I've ever been aware of, in particular in health, is the absence of discussion or even a section on the side effects of this intervention.
Yeah. Yeah, we have a proposal out right now to try to do a study in Kansas City and Chicago of gunshot detection and the impacts it has. So we want to do that. We're hoping to do that study because there's kind of some agencies kind of say this sort of thing it really helps them. Others have canceled their subscription, so it's unclear.
But that's another issue,
what this actually gives you.
I wasn't talking about the effects and side effects of ShotSpotter.
I see.
That already is, I think, this is a business. Shot spotting is a saleable business. They've been in my office many times, and they don't, I mean, someone has to show that this is affecting anything. What I'm talking about is the arrows pointing, not that they started with the ShotSpotter, which I think is
yeah, the police, I mean, I could have easily put EMS or another group there. And I mean, this is another problem, is that when a call comes into 911, we're still using humans to say where that should go. Should it go to the EMS, the police? It's and a lot of times they might send the wrong person there. So how do you alert the right person for one of these events? That's a problem that probably needs to be solved, I think, is what you're saying.
It's part of what I'm saying. I'm saying that the appropriate worker in this situation is not this as the first responder yes, for a certain part of it, but for preventing the additional events, there's a whole nother category of worker now.
Sure.
And they ordinarily are on top of this before this has gone into sequence.
As I think about Weisberg, it's mostly in Seattle and mostly didn't look at time sequence, which is what I think you were looking at. Do you have any concept of what? So they found this 4% pretty constant over time, where this 4% was located. Do you have any notion of what kind of a time interval you'd want to look at?
Yeah, this is a great question and this is the problem, is because as soon as you take a shorter time interval, then you have a small data problem, and then you have this hugely biased estimate of concentration. Right. So I have another figure that shows if you do these time series analysis that you see in the criminological literature, then they're highly overestimating concentration. And when you kind of correctly estimate it, it converges back down to just what you would have gotten if you take 10 years of data.
Yeah, the Gini index highly overestimates concentration. That was, I think, what the corrected Gini was trying to deal with.
I mean, I think they did this paper that I put on here, the first slide. Braga and Papachristos and Hiro They reported this statistic in the table, and I think this one's likely has the issue I'm talking about because their data set size was on the order of thousands, which is still too small. But then they did the correct thing where they did a negative binomial regression. And they were looking at the stability of these hotspots over time intervals, looking at what percentage stayed the same, what percentage was different. And so if you decide you want to do a regression kind of approach, then that can kind of solve this problem. I was kind of talking about what if you don't want to do regression at all? You just want to, just take the counts themselves and have this estimator of kind of this nonparametric estimator. Then this is what you can do. But you might check out that paper, which probably everybody here should read that one. It's very relevant for this workshop. Yeah.
So how do these statistics compare to the kinds of spatiotemporal scan statistics that people do looking for hotspots in epidemics?
Yeah, I mean, I think the stuff we were doing with kind of the different polygons and moving them across space is very related to scan statistics. I think the difference is in scan statistics, you drag it over all of space and then you look for this deviation from your null hypothesis. Whereas here we have a bunch of them and you want to find k of them that maximize the amount of events in those. It might be just a different name for the same thing. We didn't check to see if we were to kind of drag it across and find k of them, do we get a similar thing? The issue is that how do you kind of do that selection? Because they can't overlap, because that's kind of cheating. So it's very much related, but I don't know if they're exactly the same thing. I'd have to think more about it.
I had a question building off of what Richard said too. With a lot of crime concentration and kind of the training data needed for what you've discussed, you said almost tens of thousands for the most part would be ideal.
Yeah.
To get it going. Do you think then it's almost limited then to larger cities or high crime areas to truly train it?
Well, I think what we're seeing is that if you use a better estimator than, even a few thousand, then you can get it. And also, I kind of ignored what measurement unit in space you use. If you use street segments versus larger geographies, with larger geographies, you can maybe get a better estimate because the variance is lower if you average over a larger area. But it's kind of a coarse, then you're coarse graining it, so you kind of, eventually you'll kind of see just concentration go down because of that. But I think you can do this for data sets of maybe 1,000.
Yeah, because I imagine like rural cities that have very little gun violence, but when it pops up, it's intermittent. So it would take a long, long time even to get 1,000. And how to do with that?
Yeah, that's a good question.
Yeah. Continuing that.
I think it's one question back there. Just one sec.
I'm wondering if you can tell us a little bit or describe when you think a self-excitation model is more appropriate than the contagion model that we heard earlier. I know that your work is very different. It's geographically centered and you use different data, but I'm just curious about the pros and cons of each of those approaches if we think about gun violence.
Yeah. Well, at least one of the models earlier was the same model. It was just time-based instead of spatial. I think the problem, though, is that I think the real problem is that this background rate, right here I write it just in terms of X, but it's really in terms of time, too. There's kind of periodic patterns like day of the week or month of the year that lead to variation. And then you have longer range, like over 10 years, the economy and demographics shift, and so you have longer term periods where you have fluctuation that's not contagion. I think the hard thing is to kind of say which of these is driving that. There are other models like either these log Gaussian Cox processes, but there's other lots of time series methods that try to estimate, why do you get fluctuations in the rate of events. As we've kind of seen, at least for forecasting, those can work just as well as these self-exciting models. So which is really the cause? I mean, that's probably a question for everybody here. I don't have a good answer.
Can I just comment on that? In all contagious diseases, there are what we call sporadic cases or rare cases. So you have an epidemic of TB, and then suddenly there's a case way the heck over there, and it came out of nowhere, and it can't be linked. So what is it? It actually is that there's a very, very long incubation period. This person's exposure was years ago or months ago. And maybe the exciting event, as it were, is an internal biological event, as immunity went down or something like that. The same thing can be said for all kinds of infectious processes. So the excitability it's very similar to what you're saying in some other ways about even hotspot concentration in time or in space. You look at a larger space, you get less percentage of it. But this business of variable incubation, violence acts somewhat like TB and somewhat like cholera, because it can go very, very fast, like what happened in Rwanda. All of a sudden, a genocide, or a gang outbreak, or a war, and then a retaliation, or you get this very slow wave stuff that happens, like child abuse. Someone is abused as a child, and they grow up in abusing their own child 30 years later.
So I want to make one comment there. You brought up gang violence, and I think this is a good example of this problem. So if you take Hollenbeck, and the gangs involved in these events, and you have the network, it's very easy to see the contagion. If you take that away and just put it in space and time, the contagion parameter goes way down in your estimate. So you're no longer able to detect the contagion just in space.
Depending on how you're thinking about what the variability of the incubation period or latencies can be, which has in part to do with how you're understanding even biologically what's going on in a person, whether it's the gradual emergence of a sufficient number of microorganisms to show up as disease, or if it's a sufficient amount of whatever it is, anger or someone ticking you off or whatever. Someone who has all kinds of susceptibility, and then someone cuts him off in a car. But he has been sitting there with a certain amount of, whatever it is biologically, in terms of his ability to copy and his ability to feel whatever the expectations are or whatever trauma, because there's about 4 centers biologically in the neurological system that seem to be mediating the exposure and when it comes off. So what I'm saying, just to go back to the basics here, when you see events that are not explained in immediate, they're just there's some exposure that happened earlier, possibly, and now there's events that are not so linked to the events you're trying to link them to. Does that make sense to you?
Yeah, that makes sense, I think.
So actually, this is actually responding to that. So the way I approach that in my research with my collaborators is, if we suspect that there is a dynamic that's there that's important, we'll put it into the model, and then we'll compare statistically, fit both models to data, the one that doesn't have that effect and the one that does, and then statistically compare to see, using things like the likelihood ratio test that I was mentioning in my talk, to see if one fits the data better. So for instance, we did with the Zika virus, where it was suspected that there was a sexually transmitted component to it. And so we had data from collaborators in Colombia. And so we fit the model that did not have just was the vector-borne disease component, and then one with the additional sexual transmission component. And in fact, the one that had the sexual transmission component fit the data better. And when we looked at our contagion and mass shootings analysis, we had the model that completely was missing what's on the right-hand side there. It just had the mu-x. And then we fit the model that did have the contagion component, and we found that the one fit the data better. That doesn't mean that the model that fits the data necessarily has all of the dynamics that are important in it, but you can make statistical statements about whether or not there are dynamics that appear to be evident in the data.
Once you have something that is a contagious disease, that is to say it can produce more of itself, you should actually, and now I might be going a little further than everyone in this room would agree, you should basically assume that those are the biological characteristics of what's going on in most events, but you will not be able to determine what was going on pathogenetically, what the exact pathogenesis is in that person, as to why that person got TB now, or why that person versus that person got it. You see what I'm saying? And some of those factors we pick up as modulating factors or catalytic factors, you know, that do precipitate. You know, for example, your immune system goes down. You know, then TB shows up. I'm just staying with this one for a while. That can happen for many infectious diseases. You know, for zoster, you know, shows up later because it was dormant. You know, there's dormancy in a lot of infectious diseases. These, this vocabulary and understanding, I'm saying, is very, very important for all of this modeling, but not everything will fit because of these unknowns in the mediating or catalyzing aspects of it.
This is a great discussion. First of all, let's thank George.
Thanks.
And I will point out that this brings up a number of issues of other potential modeling approaches that we haven't talked about. So there's a whole host of multivariate methods that attempt to derive causation associated with events that I don't think we've talked about. I mean, I know them from the ecological literature, but I think some of those things, and I know Sherry's worked on some of these things, so maybe we'll talk about that. And so those would be other spatial factors. The other thing that I hope we'll have some time to talk about are issues of what we call spatial control, what to do, where to do it, when to do it, and how to assess success. And that would apply for longer-term interventions, such as putting out resources over a long time, as Gary suggested, of people who understand the sort of community dynamics, and as well as the more potential short-term kinds of interventions that may be ambulance, police, et cetera things. So it's